Well, good morning, everyone. I hope you are finding everything on the course website so that you can get all the homeworks, you can get help through Piazza. So we have 8 students who are not signed up on Piazza yet, so I will be tracking you down and making you sign up. It's the greatest way to get help. Homework this week was pretty straightforward, but I think what was the tricky part is figuring out how to get Julia going, how to fire up your server, where to go for the assignment, where's the submit button since it's way at the bottom and you've got to be at the end of the assignment to see it. But Tribby went through all of that in the recitation yesterday evening, and that is now posted on the course website underneath the lecture videos, and it's labeled as recitation, just separated from the lectures. Cool. If you have questions, you can put those into the chat or in the audience, live audience. You can just raise your hand. Otherwise, I'll go through a quick summary of where we left off. I missed you guys. I'm really glad to be back in the classroom. 5 days, it's like forever. So we've been working on matrices and vectors. They're going to be our major tool for doing mathematics at scale. And so we defined row vectors and column vectors. And then we also defined rectangular and square matrices. So a matrix can have rows, and it can have columns. Okay, n is the number of rows, goes down to here. M is the number of columns, 1, 2, 3, 4, m. If n and m are equal, we call it a square matrix. If they're different, we call it a rectangular matrix. And then the aij element of a matrix, or the ij element, I should say, is the element that would be on the ith row and the jth column. Okay, so that's where you would look. A22, A23, A31, etc. And we use them because instead of writing out equations like we have on the left, it is much more efficient for us for computations to formulate them as matrix equations. And so we typically call that AX equals B, though that may not be always the best letter there, because if you have X and Y, then you're calling the vector X. That's not very consistent notation. Okay, maybe you should call that X bar or Z or something else. It doesn't matter, you just have a vector of the unknowns, and I don't point to the boards. You have a vector of the unknowns. You have all the constant coefficients you put on the right. And then A11, you go to the first equation and you look at the coefficient multiplying x1. A12, you go to the first equation and you look at the coefficient multiplying x2. A21, you go to the second equation and look at the coefficient multiplying x1. And A22, you go to the second equation and you look at the coefficient multiplying x2. So that's how you build the matrix. Now another way to think about it, this is not something we did in lecture. So this is new material, so it's not really review, but if it's an alternative way for you to think about building up the matrix though, is you can take your unknowns, x1 and x2, and then write down in a column vector the coefficients multiplying x1, and then write down in a column vector the coefficients multiplying x2. Okay, so that's another way to think about the equation as the column vector 1, 2 times the unknown x1 plus the column vector -1, -2 times the unknown x2 equals our constants. Okay, so that's a pretty consistent way of thinking about it. And then notice this becomes the first column of A, this becomes the second column of A, etc. So Whichever way is easiest for you to see the correspondence, it's all good. It doesn't really matter. The main thing is to go from writing out equations like we do when we're first learning mathematics to then putting them into this form right here. And as we will see in homeworks 2, 3, and 4 on Julia, we'll let A be 50 by 50, 200 by 200. We'll just get these massive matrices. And if you saw 200 equations written down on the left-hand side, your mind would explode, okay? Whereas now you're manipulating an object, A, a square matrix, a vector X, a column vector might have 50 unknowns, 100 unknowns, and a constant matrix on the right. So that's how we work things in blocks of data. That helps us go to at scale. Questions so far? Anyone in the audience? Throw something in chat. Trivia will grab it. Anyone in our audience? All good? Too easy? If I'm boring you guys, tell me, speed up. Now when we're writing down these equations, it's super important, so here's how we would normally write equations. We don't write normally the zeros, okay? Nobody writes down 0x1 plus 0x2 plus 2x3 equals 7. You just don't write that down when you're writing down equations. It would seem stupid, okay, redundant. But if you're going to build the matrix, it's important to think about it that way because those are zeros in the matrix. And so let's just fill in, if we're going to think about this set of equations that I have here on the left in blue, and I'm going to look at what's multiplying the unknown x1, the unknown x2, and the unknown x3. I've already taken the constant numbers and put them on the right, saying to myself and to you that that's straightforward. So let's fill in, and let me hide that matrix there. Let's fill in what's multiplying the unknown x1, what's multiplying the unknown x2, and what's multiplying the unknown x3. Okay, so I look at my equations, and what's multiplying x1 in the first equation? There's a 0. What's multiplying x1 in the second equation? There's a 2. And what's multiplying x1 in the third equation is once again a 0. And then I look at x2 in the first equation, it doesn't show up, that's a 0. I look at x2 in the second equation, nothing there. I look at x2 in the bottom equation, and finally I have something, so I have -1. Okay, and then I go to x3 in the top equation. x3 in the top equation, I have a 2. x3 in the second equation, there's nothing. x3 in the third equation, I have a 4. So that's another way to build the matrix, okay? It's up to you. So I'm just posing that as an alternative in case how to build up these matrices was kind of scratching your head. And then we see how what's multiplying x1, that's the first column. These are all the numbers multiplying x1. These are the numbers in the matrix that multiply the variable x2. And this column of the matrix corresponds to the numbers multiplying x3. Okay, I'm getting these looks like maybe he thinks we're idiots and that's why he's going through all this in detail. I'll move on. Okay, I got it. The signal has been sent. This is where we left off. We did not do an example. We introduced this operation on square matrices. Okay, so it can be applied to square matrices. You do not take the determinant of a rectangular matrix, no different numbers of rows than columns. So The determinant is a function that maps your square matrix into a real number. So the determinant is just a scalar, minus 211, 0, 44. It's just a number. The important fact is we have a system of linear equations, ax equals b. It has a unique solution for any vector we put on the right-hand side, if and only if the determinant of A is not equal to 0. So it's this magic thing that gives us uniqueness. It's this magic thing on uniqueness. Now, when the determinant is 0, that's when things go south. You can have two possibilities. You can have no solution, or you can have an infinite number of solutions. And we did examples of equations like that on Monday of last week, and we're going to revisit those equations with the determinant as a perspective of looking at them. Okay, so we're going to see some examples of that. The unfortunate fact is, once you know that there could be either no solution or an infinite number of solutions, determining which of those cases applies when you have a 30 by 30 systems of equation is hard, but we will treat that in chapter 7. We're going to say it's not that important for the moment, because it really isn't all that important for the moment, okay? And we will treat that in detail a little bit later. Okay, so if this determinant thing is so important, how do you actually compute it? Okay, so it's this magic number. And the thing that may have left you a little bit perplexed last Friday, and maybe will continue to be perplexed for a little while this morning, is that I told you how to compute the determinant for a 2 by 2 matrix. If A is 1 by 1, then the determinant of A is just A. So now we know how to do 1 by 1 and 2 by 2s, and I'm not even going to bother to teach you how to do it for 3 by 3 and 4 by 4, etc., though a lot of classes will spend a bunch of time on that. We will develop some more sophisticated perspectives on the determinant, and you'll see why I don't want you doing hand calculations on matrices. Even 3 by 3 is just stupid. It doesn't help you at all as a practicing engineer. Fact 5 here is kind of just interesting because you'll see this in lots of books. Instead of writing det of A, they'll put straight bars around it, so you'll just have this as a notation. This is what you see in computer programming languages, and this is what you'll see in lots of books. Okay, so that's our quick, not so quick, that's our summary. So let's get going on examples. And I'll see if my handwriting improves a little bit if I sit down, because I'm kind of embarrassed how it's worked out. So if we do 3x minus 3y equals 3, and x plus 7y equals 7, so B.1, B.2 on Monday. Okay, if we write this out in matrix form, we'll order our unknowns as x and y. That seems pretty much the way to go, though you could put y first. And then our matrix will have 3, minus 3, 1, and 7. If I call this A, the determinant of A is A times D minus B times C. So it's 3 times 7 minus a minus 3 times 1. Now we've got 21 plus 3, and that's 24. We don't really care about the 24, except that it's not 0. Could have been 411, 0.91, we just don't care. It's not equal to 0. And so solution exists and is unique. And we're excited about it, so I put a little exclamation point there. Now, suppose I change the equations so that my B vector is something else. I'm sitting, so I write better? I don't know. Okay, it's not 3, 7 anymore. How does that affect the existence and uniqueness of solutions? I see people in the audience here shaking their head going, it doesn't affect at all. It's really a misdirection question just to point out, okay, once the determinant is not equal to 0, we don't care what is on the right-hand side. Anything, we get existence and uniqueness, okay? It only depends upon A, okay? I just did that to drive home that point. We still have existence and uniqueness. Okay, so later on when we get to chapter 7, I'm sure you're really excited to get to chapter 7 and as fast as we possibly can. But we will find out that the difference between no solution and an infinity of solutions does depend on what's on that right-hand side. It's how B relates to A. Okay, so that's why I'm emphasizing here, when the determinant is not equal to 0, existence uniqueness is independent of the constants, independent of the constants here. It does not matter at all. Okay. Here's another example. Minus 2x plus y equals 2, minus 4x plus 2y equals minus 2. And this was 8.1 and 8.2 on Monday, a week ago. Let's see if we're faster at writing down our A matrix. Everybody mentally do it, then I'm going to fill it in. Multiplying x minus 2 multiplying y is 1. Multiplying x minus 4 multiplying y is 2. So the determinant is minus 2 times 2, A times D, minus B times C, and that's equal to minus 4 plus 4 equals 0. Conclusion could have no solution or an infinite number of solutions. And for us right now, that's a good enough conclusion. Let's see. And I'm not really advising you to jump ahead to chapter 7. I'm just saying we are going to treat it, okay? So just be a little patient and and we'll get there. Okay? Let me do a bigger example by just pasting it in. Whoops. Insert, image, file. Bingo, determinant, 5 by 5. Oh, there we go. Where'd it go? Jump up here. Oh, here it is. May have a whole bunch of copies of it. Okay, so just yep, we do. Delete. Another one? No. Okay, so obviously don't bother writing this down in your notes. Just make a remark in your notes that there's a bigger example from the book, okay? So this is from chapter 2, so this would be equation 2.25 in the book, okay? So 5 equations, 5 unknowns, you can just check. How would you determine if there's a solution or no solution or an infinite number of solutions? Well, the first thing you do is you calculate the determinant. And in Julia, once you say using linear algebra, and you have to spell it out. I believe it's case sensitive, the package name, but that's how you do it in Julia. Once you say that, you can just say det of A. Okay, so you put in your matrix, bingo. It's minus 540. We don't care what the number is right now. It's not equal to 0, and so we've got 5 equations, 5 unknowns, it has a unique solution. The alternative, if you don't do det A, is grind it out, dude, okay? Start eliminating variables and substituting in, and if you get it right, I applaud you, okay? You must be a calculating genius, okay? So that's how the determinant is used, and we will use the determinant this way for now in Julia for anything bigger than 2 by 2. And a little bit later, even today, we'll see some cool cases where we can calculate the determinant super easily. How we doing? Everybody happy this morning online? Everybody's happy? Thumbs up in the room. I saw a couple thumbs up. Okay. Too easy, Grizzle's wasting our time. We came up here to learn something, not. Okay, so let's do, oh yeah, so now I've got that. Come on. I want diagonal, okay. Bingo. So here's the diagonal of a square matrix. Wow, I wonder why that's, whoops, hey, stay there. Wonder why it's called the diagonal, okay? Well, because it's on a diagonal, that's why it's called the diagonal. It's also called the main diagonal because all of these are really diagonals, but until you start getting into things called sparse matrices and some other things, you mainly use this one. So it's also called the main diagonal, okay? Also known as ACA, also known as the main diagonal. Because you could also look at things that are below, whoa, I didn't want to do that. You can also look at things that are below the main diagonal. You could look at the diagonal above the main diagonal, etc. For right now, we only need one of them, and instead of calling it the main G, like Grizzle diagonal, it's not called that, it's called the main diagonal. We will just call it the diagonal, even though there are other diagonals. So we're not really being very precise, okay? So that's what that is. And so if we have A equals 1, 2, 3, 4, 5, 6, 7, 8, 9, just so I didn't have to think very hard in making up some numbers. There's the diagonal, okay, so diagonal of A equals 1, 5, 9. Now, I've written it as a row vector. I think that's what Julia will give you, but I'm not exactly sure, and it doesn't really matter. If you want to stack it up and make it a column vector, nobody really cares, because really what's going to be important to us pretty soon is just the product of those terms, and we'll see why that happens, okay? So typically, when you do diag of A, it gives you the diagonal as a row vector, but that's okay. Okay, so I don't think we're going to have too much trouble with, let's see. Now, where's my learning objectives? Upper solution, learning objectives, thank you. Okay. You're hiding from me. Okay, so now we're starting chapter 3. Okay, so this is chapter 3 on triangular matrices. And the big deal here is this is our first glimpse at how we can start solving super large systems of linear equations. Okay, so practicing engineers and practicing applied mathematicians or physicists, you will not be solving 3 by 3 systems of equations, okay? It'll be more like 500 by 500 or something like that. It's going to be big. And we're going to find out that when equations have special structure, they become really easy to solve. And they'll be so easy that we can have a recursive procedure where you do this step, and then you do this step which looks almost exactly like the previous step, and you do another step that looks almost exactly like the previous step, and another step that looks almost like the previous step. And when you write it down like that, the natural thing is let a computer do it. Humans get bored when it's like that, okay? But what we want to do is set up the equations in a way that they can be solved in a snap on a computer, and that's what this will allow us to do. So we want to recognize what are triangular systems. We want to understand when we're in the case of a unique answer, and the answer about uniqueness is going to be super easy, because we'll find out that when we understand what is this thing called a triangular matrix, the determinant is just the product of the elements on the diagonal. That's even easier than AD minus B times C. Just go right down the diagonal and you multiply them. That's the determinant. Okay? We'll use 2 different ways of solving depending upon if the matrix is upper or lower triangular, and we'll deal with the permutation stuff a little bit later. Okay, let me get this out of the way. So, lower triangular system of linear equations, but we know we're doing linear equations, okay? So let's just not worry about that. So here's our first example. 2x1 equals 4. 3x1 minus 2x2 equals 6. And, whoops, need more room. x1 minus 3x2 plus 5x3 equals 7. Okay, so if these little equations were typeset nicely and the equal signs were actually in a row instead of on a diagonal, it would be easier to see the triangular structure, but it doesn't matter. We're going to rewrite it as a matrix. Okay, so let's write this nicely as Grizzle can. And we're going to stack the variables in the obvious order since they're labeled x1, x2, x3. Let's write it in the matrix form, ax equals b. Okay, so all of our constants are already on the right-hand side, so we can just copy those in here. And then this is a case where we have missing variables. We didn't write down 0x2 and 0x3, right? So we go to the first equation and we fill out the first row of the matrix. If we're doing it that way, we've got 2, we've got 0, and we've got 0 because there's no x2 and no x3. And then on the second equation, we have 3x1s minus 2x2s and no x3s. And in the last equation, we have a 1, a minus 3, and a 5 for x1 minus 3x2 plus 5x3. Okay, so we'll call this A. That's natural to call that x. Call that B. We have our AX equals B. I want to indicate the diagonal of this matrix. Everybody see the diagonal? I've done worse. Okay, there's the diagonal. So this is called A is a lower triangular matrix. Okay. What makes it lower triangular? Well, you can kind of see a triangle here, so that's why people call it, right? I mean, there's a triangle. And it's in the lower part of the matrix versus this triangle, which would be an upper triangular matrix when we get to that, okay? So lower triangular, all terms above the diagonal are 0. Okay, so that's how you define a lower triangular matrix. So this is lower triangular matrix. You look at the diagonal, and then you need to look at everything that is above the diagonal. It needs to be 0. Okay, so you recall our Aij notation. So that's the elements on the ith row and the jth column. What's the relationship we need on the Aij's so that the matrix is lower triangular? What's the relationship between the row index and the column index if I'm over here where I'm supposed to have a 0? So notice, this is the first row. In the first column, they're equal, but now I'm in the second column, that has to be 0. In the third column, it has to be 0. So the relationship between I and j here is that j bigger than I, we get a 0. Let's go to the second row. Okay, we look above the diagonal, which is just to the right. When we have on the 2, 2, that's on the diagonal, we're fine, but we need, when we're in the third column, when we're on the second row, so A2, 3 has to be 0. So that's once again j bigger than I. So this has to be 0 when j is greater than I. Oops, it's an I. Okay, so that's how you can do it. Visually, I think, you know, drawing the picture is fine. Okay, so I'm just going to paste in some more examples from the book, just because so you've got more examples, but that's a lower triangular matrix. I don't know, we could do just... Do you have the patience to write down a 5 by 5 lower triangular matrix? I'm not sure I do, but let's just try. 1, 2, 3, 4, 5. 0, 6, 7, 8, 9, 0, 0, 10, 11, 12, 0, 0, 0, 13, 14, 0, 0, 0, 0. Yay! There's a 5 by 5. Okay. Lower triangular matrix. Okay. Can I find my diagonal on here? There's my diagonal. Everything above the diagonal is 0. Okay. Question from the audience.
What would happen if you had like a lower triangle on like the right side? You know what I mean?
Mm-hmm. So the question was, and I'm not going to do, suppose we had some a tilde, and let's see if I can do that. So 0, 0, 1, 0, 2, 3, 4, 5, 6. I think that's what you're after. Okay, so here's kind of the opposite diagonal, etc. This could be used as a lower triangular, but typically people do not. Okay, so it's typically not called a lower triangular matrix. Okay, so it's what's really going on here is that there is a choice, and it turns out everything you could do with this a tilde version of lower triangular, you can also do with the other one. And if you would just reorder your variables from, if this one had x tilde 1, x tilde 2, x tilde 3, if you just flip that order and made it x tilde 3, x tilde 2, x tilde 1, it would become the other kind. So it's because you can go back and forth with such a simple transformation, we typically don't use them, but you definitely could have, okay? So it's a good observation. I've been teaching for a lot of years, and this is the first time I've ever had that question. So I hope I passed the test, Tribby. You'll have to check to see if anything I said was actually true, okay? So anything else, people? So we're going to use only the one that I have in bold A, and the a tilde, whoops, was from the audience. We're not going to use that as a lower triangular matrix. Cool. Just a few more examples so you know where to go look at them for the book. I want it to go there. Oh, I guess I didn't put them in here. Too bad. Okay. We'll just leave that, and I was going to have some more examples, and I don't. We're going to move on and start looking at how do you solve systems of equations when they're lower triangular. Okay? So the key fact that we're going to have about the determinant is that the determinant and I'll emphasize that we're using square matrices for the moment. Square lower triangular matrix. Is equal to the product of the terms on the diagonal. Wow, so that really simplifies computing determinants, okay? So A lower triangular implies det of A is A11, A22, ... ANN. You just multiply them out. Okay, so now I've taught you how to calculate the determinant of a 100 by 100 matrix, okay? Just multiply them out. And doing it for a general matrix, that would be a nightmare. Let me just say, it would be worse than the nightmare on Elm Street, if that is a social reference that makes any sense in the year 2020, which probably doesn't, but it would be a real nightmare, okay? So the determinant of, for example, let's see, I have 4, 9, 8, 6, even I have a hard time thinking I can't do better than that. 4, 9, 8, 6. 0, 2, 3, 8. See, most of the stuff is completely worthless. -1, 11, 0, 0, 0, pi, just for the fun of it. It's another perfectly good real number. Okay, Chad, we'll do that later. He's our associate director and the creator, the genius behind this course. I'm the day laborer, okay? The determinant of this matrix is, well, here's its diagonal. We just multiply 4 times 2 times -1 times pi, and we get -8 pi. And it's not equal to 0. So if we set up some equations with respect to this matrix, no matter what we put on the other side, we get that we have uniqueness of solutions. Okay, so I just want to write this down. Now, because we don't really care what that determinant is, except, is it 0? Is it not 0? So, do we really need to multiply out all of the terms and figure out that the number was really 511.6897 square root? We don't, okay? We just don't care. So, determinant of A is 0 if and only if, not equal to 0, all terms on the diagonal are non-zero. So if I have a triangular system of equations and you have a quiz and the question is, does it have a unique solution? If you actually compute that determinant, I'm embarrassed, okay? Because you wasted your time. You just look at the diagonal and check were all of the terms non-zero. And then you know the determinant is non-zero. You don't care what the number is. And then you're done. Okay? And then the determinant of A is equal to 0. And I should have put if and only if here. And I wanted if and only if here. Okay, so what's the condition on the entries of the diagonal then that I get a 0 for the determinant?
There's 1, 0.
There has to be at least one. Could there be 2? Yeah. Could there be 9? Yes. That's overkill. We only need 1. Because 0 times anything is 0, okay? If and only if at least one element of the diagonal is 0. Okay? So these are shortcuts, and they're important shortcuts when you're dealing with huge systems of equations. Now, some of you may be thinking that, yeah, it's only for the triangular case. And what I'm going to show you before the end of next week is that we can take general square matrices and break them up into triangular matrices. We're going to need to know what it means to multiply two matrices to do that. But we will reduce all algorithms for solving systems of linear equations to dealing with triangular matrices, okay? We'll reduce them all to that. And the determinant calculation will reduce to looking at diagonals as well. Okay, and then you may be the first freshman class in the nation to learn these kind of facts, but that's what we're good. That's our path to taking things down. Okay, we're running out of time, but let's get started on forward substitution. And lower triangular systems. Okay, and I leave off of equations because we're not doing lower triangular systems of cattle or anything else. Equations. Okay. So let me write down a triangular system. Whoops. As usual, my spacing has a lot to be desired. Three equations, three unknowns, man. We're not messing around, at least for lecture, and then it scales up really nicely. So my numbers are 2, -1, 6 in the first column. There's no x2s. There's -3 times x2. There's 7 times x2. So I'm thinking of that column thing when I'm writing this down. There's 0 x3s, there's 0 x3s, there's 8 x3s. I don't know where you came from, I don't want to know. 2 -7, 44. Okay, so how should I approach solving equations when they're triangular like this? Yeah. With the diagonal, we're going to isolate x1, x2, x3, respectively, in rows 1, 2, and 3. And even though I'm cheating a little bit, I'll just write this down and then we'll stop. So isolating x1, that's obvious. It's already there, but how do I isolate x2? I bring the x1 to the other side. And then 8x3 equals, how do I isolate it? Bring the x1 and the x2 to the other side. Okay, so we have to stop because I've used up my allotted time. And I'll just leave you with the idea that, I can solve here. Whoops, I didn't grab it. I solve x1, I stick it in here, then I can solve for x2. I stick in x1 and x2, then I can solve for x3, and we could just go forever like that, okay? So that's the beauty of triangular systems. We'll pick this up, we'll identify the diagonal as was suggested from the virtual audience, and thank you very much. I hope you're having fun in Rob 101, and we will continue